Hello, my name is Amanda Ricketts, and I am a graduate student at Memorial University. And today I will be discussing molecular dynamics models to better understand the interaction of adsorbed sodium atoms onto silicate surfaces. So I'll start with some background. The complete understanding of the connection between the surface and the exosphere on planetary bodies is crucial for space exploration. And we know that multiple surface processes can lead to the ejection of surface atoms, and that each process has a specified yield and energy distribution that contribute to the exosphere. So we need to understand each process to truly develop a deep knowledge of this connection. Essentially, we need to grasp these macroscopic processes at the atomistic level, which is generally complex using laboratory experiments, and therefore theoretical models are essential. Commonly used theoretical models, like binary collision approximation or BCA, require specific material inputs that are difficult to obtain accurate values for. For example, surface binding energy is an important parameter in sputtering models, and it can introduce large uncertainties into predictions when approximated. So what is the surface binding energy? It is the energy needed to remove an atom from the surface in the normal direction. And it is often approximated as the monoelemental cohesive energy, which works for pure surfaces but doesn't make sense for compounds. The different bonds found within multi-elemental substrates change the bond energy and subsequent SBE. Therefore, we need a way to determine accurate SBE values in order to obtain accurate ejection process models. Which brings me to our methodology. Inspired by these questions, we developed a method to combine atomistic modeling with BCA models. So molecular dynamics, or MD modeling, is used on the atomistic scale to study all interactions in the system. We use interatomic potentials to study the many-body effects, which means that collisions do not need to be binary and the SBE is not a direct input. And while this is great, it limits the simulation size and duration. So we propose to use MD-derived parameters in more efficient ejection models. And we've actually used this methodology to obtain a number of different SBE values for a crystalline albite surface, as shown here. Next, we wanted to apply this method to more realistic surfaces. So we asked ourselves, what about the role of adsorbed atoms? We know that if ejection occurs below the escape energy, some atoms may return to the surface and adsorb. So this introduced the questions of how do adsorbed atoms bind to the surface, and how does this affect their SBE? As well, it introduced the idea of coverage dependence on the effect of SBE on surfaces. So we developed an iterative script to first adsorb sodium atoms onto an amorphous SiO2 surface at different temperatures. Once the atoms were adsorbed, we then determined the individual SBE of the adsorbed atoms and developed a distribution of SBEs. Which brings me to our results. The results showed a large range of SBEs for the adsorbed sodium. And there was not a significant difference in the distribution of SBEs with temperature. In addition, there was not a significant difference in the distribution of SBEs for adsorbed sodium on crystalline albite as well when comparing to these results. So when comparing our results to the literature, we found that MADI predicted a binding energy of 1 to 2 eV for adsorbed sodium on a silicate surface when no free surface oxygen were available, which is obviously lower than our results. But when we look at our models, we see that the adsorbed sodium is actually forming bonds with the oxygen at the surface. This sodium-oxygen bond strength is high, thus resulting in our strong surface binding energies. However, Yikshinsky, supported by this diagram on the right, found that after the first monolayer, the sodium actually bonds metallically with the previously adsorbed sodium, and it produces this low energy desorption peak. So based on this literature, we decided to model sodium adsorbed onto a pure sodium surface, and we found this lower SBE value of 1.2 eV. So this brings into question the idea of coverage dependence. When sodium adsorbs onto a clean silicate surface, representing the 0% coverage scenario depicted to the left, we see this higher SBE value due to the sodium bonding with the oxygens at the surface. However, when we model the sodium adsorbing onto a pure sodium surface, representing the greater than 200% coverage scenario depicted to the right, we see this lower SBE value due to the sodium bonding metallically with other sodium. So what are the implications for mercury? The presence of adsorbed sodium on mercury suggests emission may be a product of coverage, and that an initial buildup of tightly bound atoms may be necessary before binding with the lower energy sites occurs. Recent models suggest that the low temperatures at the polar regions of mercury support this buildup or reservoir of adsorbed sodium. And once sodium-sodium bonds form, this drops the SBE, making ejection significantly more efficient, which brings me to conclusion and future work. So further work is required to obtain the SBE values for the intermediate coverage scenarios, including the 100% coverage scenario in which a number of adsorbed sodiums terminate the oxygen bonds. And completion of this work will help to better understand the effect of coverage on SBE and subsequent efficiency of ejection processes. And then more generally, exploring regions on Mercury, like the poles, where sufficient sodium may accumulate to terminate surface oxygen bonds could provide valuable insights. And with that, thank you.